So just a little backdrop. Basically, end of last semester, blockchain at Berkeley exploded in terms of size, and since then we've been scrambling like crazy to get all of our initiatives under lock. So last semester it was exclusively me, Philip, and Sunny running this Decal, and since then we've moved on to other things, and we've had a lot of change in leadership. We recognize that we haven't been the best about, say, posting lecture slides on the website, the videos, and being completely on top of it with the homework and announcements. So I just wanted to say sorry about that, and we're really going to try to get that on lock for the rest of the semester, because we've set up a process. That said, I feel I never really get to connect with you guys. I really love teaching this course because I think it's one of the greatest impact things that I can do. It's honestly the greatest compliment to me that you guys give me your attention for an hour and let me talk about the thing that I'm most passionate about. So yeah. So that's all I had to say. Yeah, without any further ado, we'll get on to our 7th lecture for this semester. It's going to be on Ethereum and smart contracts. So Philip is going to talking about kind of Ethereum, the technology, and then in the second half, I'm going to be talking mostly about use cases. Apologies if you are in blockchain at Berkeley, because the use cases part, you might have seen it before, but I hope you won't mind. All right.
So yeah, as Max just mentioned, I'm going to go kind of in depth into Ethereum, the technical details, how Ethereum, the blockchain and network works, how the EVM, which kind of underlies Ethereum and its execution of smart contracts, and then Max is going to jump into actual use cases where we actually apply smart contracts to the real world. So if you go to the Ethereum website today, you'll see this really fancy splash screen. And if you look underneath Homestead Release, you'll see Blockchain App Platform. And reading in the buzzwords, what does that actually mean? In fact, if you look around the Ethereum space and the blockchain space in general, you'll see a lot of buzzwords. You'll see blockchain, trustless, decentralized, smart contracts, DAOs, Bitcoin 2.0, all this stuff. But what does it actually mean? So we're going to try to kind of make some sense out of all these buzzwords, make some sense out of what Ethereum is. So looking at Ethereum from a really 10,000 feet high-level overview, Ethereum is a so-called decentralized platform designed to run smart contracts. We're going to go into what smart contracts are in a moment, but we'll leave that for a second. When I say decentralized, it's decentralized in the way that Bitcoin is decentralized, that there's no single point of control, no single point of failure. If there's a government or large corporation, we generally assume that they can't maliciously target certain actors and prevent them from sending transactions or interacting with smart contracts. Additionally, Ethereum is a so-called account-based blockchain. This is different from Bitcoin, which is a UTXO-based blockchain. And we'll go into more about what that actually means in a second. You can also kind of think of Ethereum as a distributed state machine. You can actually think of Bitcoin as a distributed state machine as well, where a block of transactions is essentially the state transition function. So going from one previous state to a new state involves generating a new block, which tells you how to get to that new state. Ethereum has a native asset called Ether. This is kind of the same as Bitcoin's underlying asset, which is denominated in terms of Satoshis. And Ether is the basis of value in the Ethereum system. It's actually needed to align the incentives of the different actors in the Ethereum system. So you have miners, full nodes, users interacting with contracts, and the Ethereum Ether is essentially used to reward miners for doing the hard work, doing the proof of work to secure the system. In the same way that Bitcoin rewards has a block reward for miners doing the proof of work. So looking at Ethereum versus Bitcoin, since we've been talking about Bitcoin a lot, hopefully this will show what is kind of the same and what is different, so you can update your mental model. Yeah? I'll actually talk about it in a second. When I say like align incentives, it's from kind of a game theoretical standpoint. We want to make sure that operating in the honest way has the greatest incentive, essentially. So you should be rewarded for acting honestly and punished for acting dishonestly. So comparing Bitcoin and Ethereum, Ethereum kind of markets itself as a smart contract platform. It's fairly complex and feature-rich. And most importantly, is it has a Turing-complete scripting language. This is compared to Bitcoin's Bitcoin script language, which is actually not Turing-complete. It's a stack-based, very simple language based on like Forth, essentially. And what that means is that in Ethereum, with the scripting language, you can actually define essentially arbitrary computations. And these will run, in the magic blockchain, and you get incredible power from that. And of course, if we remember Bitcoin, Bitcoin is it's really more marketed as a decentralized asset. So for the most part, that means you have a stable currency that people trade between each other. What's important to note, though, is that both Ethereum and Bitcoin have like decentralized assets, and they both have scripting languages. They are just targeted towards different use cases. So one really interesting thing to note is that the Ether asset is actually not necessarily a primary goal of Ethereum. Really, it's kind of a side effect of having an incentive-aligned smart contract platform, and also acting as something that smart contracts can trade between each other. And just as kind of a side note, we've talked about the mining reward in Ethereum. Ethereum is actually planning on moving to something called proof of stake, which is essentially where you're rewarded for having a certain percentage of the overall stake of the capital in the network. We'll talk about that in, I think, lecture 8, the next lecture, whereas Bitcoin is probably going to remain proof of work for the foreseeable future. And some minor miscellaneous implementation details. So Ethereum actually has a really short block time of only 12 seconds, as opposed to Bitcoin, which has a 10-minute block time. And part of the reason for this is that Ethereum wants their smart contracts to be, when you say to a smart contract, like, do something, you want it to happen quickly and not like 10 minutes from now. Of course, this is kind of debatable, but it's also arguably at the expense of security. Ethereum has a very complex system for dealing with orphan blocks. They essentially reward miners for finding orphan blocks, or so-called uncles, which is maybe more in-depth than we'll go into in this lecture, but it's something to look at if you're reading the white paper, the yellow paper. They also use different proof of work algorithms currently. So Bitcoin uses SHA-256. Ethereum uses something called ETH-hash. Currently, ETH-hash is ASIC resistant, so it's, as of right now, not economically feasible to write or create specialized chips for doing the Ethereum proof of work function. And that is, an arguably a decentralization force, which is in some people's minds a good thing. Also, the exchange rate is pretty different. Ethereum, I think, is the second largest cryptocurrency. The current exchange rate is about like $17 per Ether versus Bitcoin's like 1,200 or something currently. So previously I mentioned that Ethereum relied on an account-based model as opposed to a UTXO-based model. And what I mean by account-based is essentially a single entity on the Ethereum network, so like me, for example, has an account. And that account has some balance of Ether, and an address by which you identify that account. And this is contrasted with Bitcoin, where there are no necessarily accounts, where I as an entity own a set of UTXOs, or the private keys to the addresses of the outputs of some UTXOs. And that actually defines the amount of Bitcoin that I hold. Whereas in Ethereum, you have an account that defines how much Ether you hold. So this is kind of a subtle distinction, but it changes the way that we write smart contracts. Ethereum actually makes a subtle distinction about two different types of accounts. There are externally owned accounts and contract accounts. Really under the hood, they're pretty much the same thing. One just has code and one doesn't. Externally owned accounts are basically what a person or a corporation would own. So that account basically just has an address and some balance. And those externally owned accounts can send transactions to other Ethereum accounts or contracts. Contract accounts, however, have not only an Ethereum balance and an address, they also have code associated with them. And this is the smart contract part. This code is essentially what lives in the blockchain and execute in a distributed, decentralized manner. What's important to note is that in Bitcoin, the entire state of the network is defined by the UTXO set, the unspent transaction output set. In Ethereum, the entire network state is defined by the entire account state. So the state of every account is essentially the entire network state. So that means for every account, the current balance, the address, the persistent storage, the code of every single account is encompasses the entire state of the Ethereum network. And again, thinking of it as blocks as transition functions, the Ethereum network state is essentially updated every time a new block is generated. And that block contains transactions which either send Ether to different accounts or maybe trigger a smart contract to do something. And kind of the rationale for Ethereum using this account model is that it actually saves space as compared to the UTXO model. So in the UTXO model, you have to save the unspent transaction outputs of every single transaction, whereas in the Ethereum model, when you see a new transaction sending money from Alice to Bob, you just update the balances in Alice and Bob's accounts. And so you don't have to continually add new unspent transactions to the mempool. It's also really just more intuitive when you're writing a smart contract. It kind of makes more sense to people to write send money from Alice to Bob as opposed to gathering up some dynamically changing set of UTXOs that Bob owns and then sending that to one of the addresses that Alice owns. That's kind of hard to program easily. So previously I mentioned that Ethereum is a smart contract platform. So what actually is a smart contract? If we looked at what a regular contract is, it's essentially an agreement between two untrusting parties that can later be actually enforced by a court of law. So for example, a futures contract is something where you say to someone oh, if I will give you this much now for the future that some derivative will reach a price and then we can trade on that. And essentially that contract, if everyone agrees and it goes out well, the money changes hands, it's all fine. If someone, reneges and doesn't send the money, then you can sue them. And, the court will force them to send the money or something. A smart contract, on the other hand, is essentially encoding that logic into into code, essentially. So a digital contract. Without something like Ethereum, you basically need a trusted third party to execute this contract and decide on who gets the money or whatever. What's really cool about Ethereum is you can essentially remove that trusted third party and replace it with the Ethereum network. And so this contract, this smart contract, runs in the context of this global distributed network, and everyone can agree on what happens with the contract. So again, in Ethereum, smart contracts are executed by the network. So every single node on the network every full node, all the miners, actually execute essentially the code in each contract when like a function is run. So, and this happens in lockstep across every single node. So it's like parallelly redundant. So every node is updating the same state at the same time. And this kind of ensures that no one violates the contract because everyone agrees on what the contract should do. And again, there's no trusted entity because we kind of assume that the proof of work forces everyone to cooperate. So let's see. Okay, so one way you can kind of think about smart contracts is as these like autonomous entities that live in the magic blockchain land. And they essentially don't do anything until you give them some sort of external stimuli. So, and the way we do that is by basically poking them with transactions. And those transactions have some sort of metadata that says like call function foo or send money from Alice to Bob. And each of these smart contracts is actually just an account. And so because those smart contracts are just an account, they actually have control over their own address, their own ether balance, and their own permanent storage, et cetera, et cetera. To kind of classify Ethereum contracts into several distinct use cases, there are contracts that generally like store and maintain data. So for example, you'd have a token currency or a domain name registrar, which Max will talk about later. There are other contracts which kind of manage relationships or contracts between untrusting users, and the keyword is untrusting. And so these are generally like financial contracts where you have different parties that don't necessarily trust each other but want some sort of common code to run, or escrow and insurance where it's easy to have other parties that would cheat, and so you want to make sure you have like a single source of truth that executes and maintains that integrity. So there are other contracts that are essentially acting as software libraries. This is kind of a obvious case, I guess. And then there are other contracts that do more complex authentication. In Bitcoin, we've talked about M of N multi-signature transactions. So you have you need M parties of an N-sized group to cooperate to perform some function or send some money somewhere. So if you have like a board of a large corporation, and maybe you trust that like no more than 5 board members will collude out of like the 10 board members in order to like send money or create a new proposal that the corporation will follow, for example. And then a lot of smart contracts are just combinations of these specific classes. To kind of give an example of what a smart contract looks like, we're going to look at what I call the minimum viable token, or Philip token. Essentially what this contract does is it creates its own cryptocurrency called Philip tokens. And what these Philip tokens can do is you can instantiate a new instance of the Philip token currency with some initial balance. And then you can actually send Philip tokens between people. So if you I don't know if you can read the code, but you can see in the first function, the constructor essentially, you create a new instance of the Philip token currency with an initial balance. And that basically sets the balance of the creator to that initial value. And that person can then transfer Philip tokens to other addresses. And it checks that there's enough money in that person's account, reduces that value from their account, and then increases the value of the recipient's account. So this is kind of a very simple example of what's actually pretty powerful. This is a distributed currency. You can trade it between whoever. There's no government or corporation that controls it. No government can control what or who you spend the money on. And so this is like the most basic example, but we'll show some really, really interesting use cases later on. So one thing I'm going to talk about next is the Ethereum virtual machine. And this is actually how smart contracts are executed on each of the nodes. So the Ethereum virtual machine is what runs the contract code. The actual contract code that gets executed is not the high-level scripting language that's like shown up here. It's actually a very low-level bytecode essentially. It's like a stack-based language. It's actually very similar to like the JVM bytecode language, but it has some additional features and kind of targets a different use case. And one thing to keep in mind is that every single Ethereum node actually runs the EVM on all of the transactions in a block every time they run the block verification procedure. And this is how they update their internal state to match the new network state. We can actually think of the EVM as the underlying state transition mechanism for each of the nodes. So you basically start off with the current block state, the gas required, the memory of the contract, the transaction that's like calling the contract, for example, the message, which is essentially the additional like metadata of the transaction, and then the code of a contract, the stack of the contract, the program counter, and basically all of that gets fed through the EVM, and you get the new block state with all the updated balances and internal state, and the new gas value, which is essentially how much gas is left over, which then gets added back into the account. So some of the design goals of the Ethereum virtual machine are simplicity, space efficiency, determinism, specialization, and security. So the EVM code was actually designed to be just as simple as possible, really minimize the number of possible opcodes. And this actually helps with static verification of contracts. So there's actually a paper written by Microsoft that goes over how to easily statically verify contracts to make sure they execute correctly. Also, because the opcodes are simple and minimized, we can have much smaller bytecode sizes that represent each opcode, and this gives us space efficiency. Determinism is an important factor because we want every node to execute the contract code in the exact same way, regardless of what the underlying architecture that node is running on. So if that node is a like x86 Intel CPU or an ARM CPU, either way they should execute the contract code the same. The EVM code is also specialized to handle cryptography, essentially handling like 20-byte addresses easily, handles modular arithmetic, and reading block and transaction data. It was also designed to be secure, so there's no way to like overflow the Ethereum virtual machine and like take over a node, for example. How the kind of code pipeline works is that we start off with the high-level scripting language that we showed in like the Philip token, and then that gets compiled by a like Solidity compiler or a Serpent compiler in case of the like Python like contract code, and all of that gets compiled down into the EVM code or the like simple stack language. And that EVM code is actually what gets run on each of the nodes and pushed onto the blockchain. So one like immediate question that might pop in your head is, what if that contract has an infinite loop? If you think about it, all of a sudden this contract is pushed onto the Ethereum network. Someone calls the function foo, for example, and now every single node sees this transaction, starts executing foo, and then they execute foo forever. They're stuck in an infinite loop. Like, that seems like a pretty obvious flaw. And this actually brings us into the reason why Ethereum has gas. And you can see pretty clearly that with that infinite loop, it'll be like a denial of service attack because you essentially force all of the nodes to execute forever. So this brings us into why each of the contract functions require a certain amount of gas, and this gas fuels the execution of that code on the nodes. So the way they essentially build that up is so each function is composed of a number of opcodes, and each opcode costs a certain amount of gas to execute. So in order to execute like an add opcode, for example, it might take like a couple way of ether, essentially. And so when you create a new transaction to interact with the contract, it actually specifies the start gas, which is the maximum amount of gas that transaction is willing to consume, and then the gas price, which is like the kind of the exchange rate of gas to ether. And so at the start of the contract, you basically take the start gas, multiply it with the gas price, and that is the amount of the total or maximum amount of ether worth of gas that you're willing to spend on that transaction. And that's subtracted from your account. If the contract runs successfully and completes, there might be some leftover amount of gas, and that's just added back into your account. However, if the contract actually fails to execute because you didn't put enough gas into it, it'll actually revert all of the execution of that contract and essentially won't refund you any of the gas. So you should always kind of overestimate how much gas you're willing to put into the contract. So this brings us back to the infinite loop. Ethereum actually still allows the infinite loop. It just requires that you have enough gas to fund it, which is impossible. So if you're trying to run a denial of service attack, you basically have to front enough money to keep like these malicious contracts running and holding the nodes up. Of course, hopefully this should disincentivize denial of service attacks because it'll be very expensive. And you can kind of think of buying gas to fund these contracts as buying like distributed trustless computational power. So one important thing to note about Ethereum is that it's not optimizing like computational efficiency necessarily. Instead, it's really targeting a different use case where it's optimizing for distributed and trustless execution. So all of these transactions are run across every single node in the network, so it's redundantly parallel. And this really gives it an efficient way to reach consensus in this network. And because they are redundantly parallel, it's actually very expensive, and that's why you shouldn't be running like machine learning or something on your Ethereum contract code. And hopefully this gives an incentive for computation heavy computation that can be done outside of the blockchain to not be done on the blockchain. So with that, Max is going to talk about some smart contracts and their use cases.
All right. So here's a quick splash of some buzzwords that you might see through the rest of the slides. Okay, so to start with basic use cases, Philip kind of already covered this in his example of Philip token, but one way that Ethereum likes to market itself is like, look, we can implement Bitcoin in 4 lines of code. All you need to do is, it's a database with one operation where you just need to check that this person has enough money, and then if so, subtract it from Alice, give it to Bob. If you may recall, last year there was a point where sites like Twitter were going down. I think this also happened earlier this year. Basically because their DNS servers were getting DDoS'd. So what if you implemented a decentralized registry? So all you need is some kind of key value store. So you can map a domain name to an IP address. I can map my personal website name to 696969. And the benefit of this is that it's immutable. It's distributed across the whole network, so that if random nodes across the network were shut down, you could query the other nodes remaining to still get the correct IP address for your service. And here's just some example code. Very easy implementation in Ethereum. It's very powerful. Here's actually a hackathon project that me and Philip did last year. In general, Ethereum allows for trustless incentivization and crowdfunding. So we created a smart contract where these contributors can pool money into this contract that's going to pay out to some specified recipient if and only if they vote that this recipient completed some action by some due date. So our example use case of this is if a company is polluting some river nearby and the residents are unhappy, they're willing to pay for this cleanup because they're bearing the negative externality. So what they can do is, if the government's not responsive, unwilling to help, they can set up one of these smart contracts that's going to pay out to the company only if the company cleans up the river by this due date. And this solves the free rider problem because the free rider problem is you don't have a guarantee that the other people in the economy or whatever, the other actors, are also going to contribute to this thing that everyone wants. So by allowing people to commit funds in such a way that they can withdraw their funds if this doesn't actually meet the threshold, all trustless, you can implement a lot of cool game theoretical solutions directly in Ethereum. So moving on to some more advanced use cases. So imagine if you have some smart energy grids. The basic problem is that in a neighborhood, there's some imbalances in energy across the community. So one house might have excess heat while another might be too cold. And the ideal solution is you have this house that has excess heat sell its heat to the house that's too cold. And therefore, you can cancel this energy difference and make the community more power efficient overall. So in other words, you're also just creating an energy market, right? But the thing is, you need custom infrastructure between these houses, from house A to house B to house C. And the current infrastructure only flows unidirectionally from the utility companies to the endpoints, the houses. And this utility company is not going to want to build this smart grid infrastructure because it means they get less revenue. Because if the houses are buying energy from each other, they can't scrape a bit off of profit off of being the intermediary. So also in this case, the government is usually too slow or unwilling to help. Like, what does the government get out of this? But it's purely these peers that are going to benefit from this. So they can set up a Ethereum smart contract that will enable basically like a financial commitment. So in your smart contract, you can encode this logic. I, house A, am going to commit $10,000 to building this infrastructure. If house B and house C also commit this amount, then this amount will go to this contractor and only this contractor. And here you can read the terms in the contract and trust that it's not going to be violated. I can't take your funds or anything like that. So basically, you're using the Ethereum blockchain as a coordination layer. When you can't have coordination from some government or central entity, you can fall back onto the Ethereum blockchain and implement a technological solution to what was originally a social problem. Okay, so decentralized prediction markets. This is one use case that the techies tend to really like. So what is a prediction market? It's basically drawing on the wisdom of the crowd to try to forecast the future. It's been shown that prediction markets usually do better than pundits, experts, because when you spread out through the crowd, there's usually some people in that crowd who have additional information about this event, and by allowing them to make money off of that, you get a more accurate forecast. So what you do is you have these market makers create this event. So for example, who is going to win the 2020 US presidential election? This actually used to be 2016 and Trump and Hillary, but and the caveat is that these events need to be public and easily verifiable with a set due date, and we'll see why in a moment. These participants are going to buy shares. Okay, I think Trump is going to win, or I think Zuckerberg is going to win. And they're going to pay a small fee to do so. And on the election day, you have random oracles spread out across the network who will vote on who won. So the oracles who vote with the majority take the fee that was paid into that market. Otherwise, they're penalized and might lose their status as an oracle. And the shareholders who voted correctly are able to cash out on their bet. Yeah.
What's an oracle?
Yeah. The question was, what's an oracle? An oracle is a entity within this prediction market ecosystem that reports on the outcomes of real events, basically bringing data into the blockchain. Yeah, you'll hear that term a lot. So to kind of give you guys a better mental model of like what exactly prediction market is, you can simplify a bit. You can say that, okay, the share price for each market accurately represents the best predicted probability of some event occurring. So if the share price is trading at, say, 63 cents, then the market says that there's a 63% chance that this event is going to occur. And to simplify this, you say that these shares will resolve to $1 if the event turns out to be true. So you can cash it out for $1, Otherwise, it cashes out to $0. So in this case, if the shares for Trump and Zuckerberg are currently trading at like 50 cents, and I think I have some dirty information on Trump that I can release during the election, and I think that Zuckerberg's chance of winning the election is actually 70%, then what I can do is I can buy these shares, for Zuckerberg at 50 cents until the share price goes up to 70%, and therefore I've acquired shares that were worth 70 cents at the price of 50 cents. And based off of the expected value, I've made money off of this arbitrage using information that I had. So the powerful idea with decentralized prediction markets is that you can finally escape all these silos, of only allowing people to bet on, say, political events, because people always talk about politics. What if you could do things like, okay, create a market, like, will this Hollywood movie be a flop? You can bet for and against this event to create some liquidity, and then once these Hollywood insiders see this, they're like, oh, I know whether or not this movie is going to be a flop, and they can bet on whatever side of the trade is beneficial to them, and therefore you've essentially bought this information from them. You can also use this for use cases like hedging and insurance. So whenever you buy fire insurance, you're basically betting that your house is going to burn down. So you can create a market that says, is my house going to burn down, and vote yes. And some insurance company is going to think, oh, I don't think that that likelihood is that high. I'm going to take the other side of the bet. So if your house actually burns down, you're going to receive all the money that they put in. Obviously, there might be some issues with moral hazard, but this is just kind of to illustrate like a theoretical construct where we could even implement an entire insurance liquidity pool onto a smart contract and avoid the high costs of having offices and people manage all of this. So yeah, just interesting ideas that blockchain makes possible. There's other things you can do, like setting up a security bug bounty. So you can say, like, is my company going to be hacked by this date? And then just bet very heavily against it to incentivize these hackers to try to hack the company. And then whoever finds this vulnerability, they're going to buy these shares and then perform their hack and then receive a profit. Therefore, like, now you know like what the hack is, well, presumably, and you've basically been paying for your security. And it's interesting because Augur actually secures their own code this way. So, oh, I forgot to cover. Augur and Gnosis are the most well-known decentralized prediction markets today. Augur had its token sale sometime in the last half year. You can go on the Augur website and look at the events and bet on things if you're interested. Yeah, another thing you can do with these decentralized prediction markets is you can signal, like that term, put your money where your mouth is. For example, if you have a Kickstarter campaign where your investors are worried whether or not you're actually going to deliver your product on time, you can create a prediction market that says, will my product launch on time? And then bet very heavily that you will launch on time, because now you're willingly exposing yourself to this financial risk and saying like, hey, I'm willing to lose this much money if I don't launch on time. Therefore, I am proving to you that, okay, I will do this. So to kind of analyze this, the main benefit to being decentralized is that there's no restriction on market creation. Instead of only betting on sports and politics, you can now bet on insurance, security, hedging. But the thing is, there's a caveat. You need to implement some kind of defense against unethical or illegal markets, because presumably you could set up a market like an assassination market. Like, is this person gonna die by this date? And then there's a lot of moral hazard there. So Augur actually implements something where an option when they vote, they can categorize it as unethical or undecidable if there's no clear outcome for the event. The other thing is that you can have a shared liquidity pool. So say you wanted to bet on politics. There's no reason why you need to be betting on politics in 20 different exchanges across the world. They could use Augur and Gnosis as a backend and just provide the front end and cover all the regulation at the endpoints when they're actually offering the services to people in that country. This is censorship resistant, and it also allows for automatic trustless payments. You don't have to trust that the prediction market platform is going to steal your funds in some way. There's also some explorations in this idea of decentralized IoT. So there's a company called Filament, which is building the blockchain-based decentralized Internet of Things, ad hoc mesh networks of smart sensors, lots of buzzwords. But basically, they're building these sensors that have a 10-mile range with a battery life that lasts for years, and don't even require an internet connection because they just use mesh networking. So they want to deploy this in agricultural fields, want something really strong and robust. And it's interesting because they implement blockchain as one part of their technological stack. So they use the blockchain only for the name address binding. Like, okay, this device is bound to this this asset on the blockchain. And by doing it on a blockchain, they're taking advantage of the fact that these bindings can be incorruptible. And if you wanted to fake a proof, it's cryptographically hard to do so, versus having this all stored on a central database where someone could hack into it and make modifications without anyone knowing. So the main reason Filament is a decent application for this is because it emphasizes resilience and dependability. The data for these bindings is duplicated across a lot of nodes. You don't have to trust some central server, and if you want something that is very durable, you want it to be redundant. All right, so this is also an idea that I've had recently. Basically, is this 24-hour stock trading would be really convenient, but it doesn't exist. And this is strange because we live in a highly digitized world. We have a world where we have Amazon Go stores where we can go in and take things and walk out with machine learning. But why don't we have 24-hour stock trading? This seems like a very comparatively simple problem. And the problem is just there's not enough liquidity. Because there isn't enough liquidity, the price is more volatile and destabilizing. And the government sees this, okay, that's dangerous. We're going to restrict trading to only limit orders. We don't want this kind of financial instability. And this is only sustainable at larger brokerages where there's enough stock to sustain any kind of market, because you have to trade one particular stock, right? To quote the Direct Edge COO, he says, convenience is great, but I'd rather have a better price, better price discovery in this market. So the solution is that you can implement a blockchain-based asset exchange with legal bindings from the exchange, the actual assets, to the brokerages themselves. The mechanics of this would be you have these brokerages let users withdraw their stock into these stock tokens onto a blockchain, and this stock would be subtracted from the user's account, and in the meantime, this brokerage is just going to hold it. So the brokerage will write a legal contract, like a U.S. government, enforceable contract that says anyone who proves that they own this stock is eligible to redeem it for a stock that I am currently holding. And therefore, you've created this ecosystem where all these tokens on the blockchains are backed by a real stock. And now you can create a trustless blockchain-based stock exchange that allows users to trade these stock tokens, any users to trade these stock tokens. And you've now built after-hours trading with very little cost. You've also opened up this market to anyone in the Ethereum ecosystem because now instead of having to register at a brokerage, if you own any amount of Ethereum, you can exchange that Ethereum and on this trustless exchange, buy your assets, and then once you want to exit your position, exit back into Ethereum. And now you've enabled trading for a whole new world of investors. And if you have multiple brokerages participate in this, you have now a shared liquidity pool. And in addition, they don't even need to trust each other since the blockchain is going to manage everything okay, make sure no one's double spending, make sure you're following all the rules of stock trading. And from a regulatory perspective, you can enforce this anti-money laundering when the traders actually redeem their tokens. So similar to how in cryptocurrency exchanges, they don't basically require any information from you when you're just trading crypto assets. But as soon as you want to convert a crypto asset or cryptocurrency into US dollars, then they suddenly ask for like, oh, what's your, your passport, your social security number, your driver's license. That's how you, in general, enforce regulation in the blockchain space. Last kind of use case is a decentralized autonomous organization, and it's basically a organization that's governed entirely by math and code, where the entities may be people, they may be computers, they can be whatever. These entities can create and vote on proposals, and theoretically you can have businesses that exist entirely on a blockchain, paying for all of the input costs on a blockchain, and producing all output on the blockchain. There's some uncertain legal status, probably just because the space is so new, but the general notion behind DAOs is code is law. Trust in math and code as opposed to governments and institutions. Some issues with this is that it's really hard to edit the governing laws once it's deployed, because you have this immutable smart contract. Possible solution to that is to create a child DAO. But it's interesting because if you've heard of something called VDAO, it was actually the largest crowd-funded project in history. And because they implemented a child DAO, they basically exposed themselves to an attack where like $60 million worth of Ether was stolen, which was actually worth 10% of the Ethereum market cap at the time. There's another use case, another example of a DAO is Dash. So Dash is a privacy-centric currency where part of the mining rewards actually goes into this kind of like this collection where these masternodes can then vote on how they want to allocate these resources for the further funding and development of Dash. So it's a self-sustaining ecosystem that still maintains its decentralized architecture versus some other cryptocurrencies that have something like a founder's reward where a bunch of money is going to go to this specific group of people, and through that mechanism it's pretty centralized. So in the last few minutes, I'm going to try to make some generalizations about blockchain tech. Main limitations is that there's no trustless way to access outside data. Generally, you need to rely on oracles, but then these oracles themselves may be trusted. So one potential solution to this is you have proven execution. So basically, you can prove that some HTTPS page existed in your browser at some point in time, and then it's like, okay, therefore I know that this HTTP call wasn't manipulated by the person reporting it to the blockchain. The other potential solution is to implement an oracle network, just like what Augur does, but there's a lot of edge cases and incentive compatibilities that you need to be really careful about because you're basically implementing a consensus protocol on top of a consensus protocol. The other thing is that you can't enforce on-chain payments. It's meaning you can't, borrow from a contract and then trustlessly have it returned. It's kind of like violating the whole notion of borrowing money. One compromise you can have with this is to implement a decentralized reputation, like a credit rating on the blockchain. And in addition, these contracts can't manipulate confidential data. So whenever you have confidential data on Ethereum, that means someone's computer across the world, a lot of computers across the world are having this data on their hard drive. And if they're able to manipulate this data, that means they can go into their hard drive and read this data. So for apps where privacy is a big concern, you probably don't want to use a blockchain. The only thing you can kind of do is encrypt the data before you put the data onto the blockchain, but then you can't manipulate it unless you have something called homomorphic encryption, which is still a research area. So just going to conclude with this slide. These are basically the essential properties of blockchain killer apps. I tried my best to kind of summarize the key points, the oases in this desert of use cases where blockchain tends to shine. So trustless environments that need consensus or coordination. So you can think Ether on a stick, the crowdfunding platform, the smart grids that need to come to consensus. Disintermediation and censorship resistant, like getting around that utility company. And blockchain allows you to have like data that is correct by design. So in general, if you have some expensive human-oriented process where the rules are fairly well-defined and you think perhaps a market might do this better, you can implement those rules onto a smart contract and just release control, and you can trust that it's going to be enforced. Just kind of skipping through this. It's really good for robust systems because it's so redundant. And new ways of creating incentives, like Ether on a stick. And this is still really new, but new governance models are also possible. The whole notion of blockchain and decentralization, obviously contrasts with centralization. So the points where centralization tends to shine is whenever you want to have deep integration or some kind of cohesive user experience. Like, for example, Facebook owns all of our data. And because they have all this data in one place, they can run machine learning algorithms on it and optimize our experience for everyone on the platform. Versus if you were to implement, say, a decentralized social network, everyone has control of their own data. And there's not enough data to really run those cohesive, integrated applications. In general, only in a centralized system can you have good control over read and write permissions, because fundamentally, in a blockchain system, you're taking a central database and distributing it, and everyone now has access to that data versus one person who can kind of act as a gatekeeper. Also, centralized solutions tend to manage complexity really well. So for example, why don't we have a decentralized Airbnb? It's because in a case where they need to resolve a dispute and you need human level judgment to analyze evidence or whatever, that's very hard to encode into logic onto smart contract. Yeah, so that was it for today. I don't want to keep you too long. Your homework is to write a half-page paper on smart contract or decentralized app use case, talking about why you think this would be better than a central database. We released the prompt on Friday, and we finally locked down our airdrop. So Aparna has your free money. Thank you for not leaving early because they got gypped. So yeah, okay, here's the readings for next week. Thank you. All right.